So thank you for inviting us to speak at Scale Up 360. My name is Albert Lee. I'm a senior software engineer at AdaCore, and I'm based out of the very calm and peaceful city of New York. Um, anyway, so today we'll be presenting this presentation on confident algorithms with formal proof techniques. So the whole idea behind this presentation is that in the last few years, formal proof has become more accessible to regular professional software engineers. A developer can now code up expectations in source code, and then using a tool that feels like a compiler, these expectations can be proven to hold so that you can have a lot more trust in your software. And furthermore, moving a lot of this verification work earlier in the development cycle reduces costs. You can have so much confidence in your software that it's even possible to forego testing, and you can reliably replace tests with proofs of program behavior. And let's explore this a little bit. So here we have a very simplistic diagram of a fictional sensor fusion software stack. But for illustration, the layers can look something like this. At the lowest level, you have the hardware, of course. And then the first software layer right on top of that hardware is going to be either an operating system or a BSP on bare hardware. On top of that, you have gear that interfaces with that hardware and provides that first layer of abstraction. So you have device drivers and a hardware abstraction layer. Uh, and since this is a sensor fusion application, you'll have a sensor fusion layer. The sensor fusion layer talks to the drivers and the various hardware and attempts to create a sort of a unified picture of the universe. And then on top of that, you have behavioral decisions being made. Generally, we see C being used for lower level stuff and C++ being used for higher level stuff. Our specialty at AdaCore is the Ada programming language and the Spark programming language. And Ada and Spark can be used very, very efficiently and effectively for the entire stack at every layer of abstraction. There are features in this language that are suitable for low-level programming, and there are powerful facilities available for programming in the large. So let's show you real quick what the language sort of looks like. All right. So initially, let's start with something that everybody's familiar with. Here, you have a software interface to a UARTs control register. So you've got an 8-bit byte, in this case, that's mapped to a certain location in memory. And using this control register, you could control the baud rate, the parity, and whether the device generates interrupts. Now, in the C code on the right, on the top, well, it's like 2/3 of that column, you see a bunch of constants that are defined for you to use. And then on the bottom are all of the masks and shifts for setting the baud rate and setting the parity. Now, it's really important, if you're the developer here, and the C people with experience in C know this, it's really, really important to use the correct combination of the ands and ors and nots, the Boolean operators, the bitwise Boolean operators, and to use the correct shift and rotate operators. You have to use the correct symbols, the correct syntax, using the correct constants, of course. Now, you have to do all of that with an accurate picture of the underlying hardware representation in your head while doing all of that. So here is what a similar thing looks like in Ada. In Ada, it's possible to generate comparable machine code using source code that's a lot more powerful and expressive. So the code that you see here written in Ada is portable. The same code can be retargeted to different hardware and will work exactly as written. It's reusable, therefore, and it's hopefully to everybody here, it's readable, and it's certainly very, very precise. Let's go through what it looks like, what this all means. In the left column, we have these two enumerations. You know, we have these three paragraphs. The two first ones are enumerations. First one says type baud select is, and that's just Ada's way of specifying an enumeration. And then you have a clause that says with size 3. That with size 3 is an aspect in Ada. And this particular aspect, the size aspect, tells the compiler that baud select occupies 3 bits. If you skip down below, type parity select is pretty much the same thing. This one occupies 2 bits. For each of these enumerations, you see for baud select use blah, and for parity select use blah. That those things are called representation clauses, and they define the actual hardware values to be used for each enumeration literal. Now, on the bottom of that first column, you see that clause type bits 2 is mod 2 to the second, right? So that star is exponentiation in Ada. And what that does is it defines what we call in Ada a modular type, which in any other language is called an unsigned int. In this particular case, with this type, however, we do attach that aspect of size being 2. So this values that are supposed to fit in this type will be anywhere from 0 to 3. Now, once these basic specifications on the left are coded up, we could do all the stuff that we do on the right-hand column. So we assemble all of those chunks into an Ada record, which is just like a C struct. And an Ada record is able to do a few more things. We have these aspects attached to this particular one. We say with volatile full access, which means all accesses to this, all the reads and writes must be done atomically. And we say that the size is 8 bits. Well, that's interesting. You have 4 fields in this record, and the size of the entire thing is 8 bits. The next paragraph down has another one of these representation clauses, and we can actually lay out bitwise all of those fields in that record. We say that baud occupies byte 0, and it occupies bits 0 to 2 of that byte. Parity is also at byte 0, but it occupies bits 3 and 4 instead, and so on and so forth. So now we have this really, really precise definition for the register. We've got names for everything. The compiler has enough information so that you as a coder, you as a programmer, can just use these names. All the logic and all the math can be constructed automatically and correctly. And there's no loss of efficiency. The compiler is going to do what you would have done anyway, or maybe even do something better in a little more optimized way. So next, we define a variable of that type. You have the uartreg of type uartcontrolreg, and we have an aspect with address, and we map it to that constant 8000 hex. And so now we have this variable that's been mapped in memory. The most beautiful part of this entire slide happens in the last 2 lines. Now, we did all of that work, we did all of that work to specify what the interface looks like, what the software interface to the hardware looks like. Now, the actual operations of setting the baud rate and the parity are just assignments. uartreg.baud is assigned B_115K, and uartreg.parity is assigned even. The compiler does all the stuff. The compiler does all the error-prone stuff correctly and efficiently. The programmer is not responsible anymore for using the correct combination of Boolean operators, shift and rotate operators, using the correct symbols, the correct syntax, the correct constants, while keeping that picture of the underlying hardware representation in mind while doing all of this. All the programmer really needs to do is assign values to variables. In our view, this really is the right way to program. Spend work defining a very precise specification at a very low level of abstraction, and then you use that spec at a higher level of abstraction. When you do that, the programmer has an easier time being correct about everything at every level of abstraction. Right? Now, similarly, if you have some hardware that, like a peripheral, like maybe a network device that provides data with a byte order that differs from your processor's byte order, normally you'd have to code up some swap routines. Not only do you need to make sure that these routines are coded correctly, but you also need to make sure you don't do anything silly, like swapping something twice, because I've never done that. So in our Ada Core's Ada compiler, we have an aspect called scalar storage order. And what that means, by using this, you don't have to code up your swap routine. You don't have to code up explicitly. You don't have to code up any swap routines. But that's not really the big deal. The really big deal is not that you can get away with a little less coding. The really big deal is that now the specification of the data register type is so precise and correct that it's harder for you to screw up. What you can do here, you have a variable of type data register, a variable data of type data register. And as a programmer, you just do stuff with data directly. You don't manually have to swap things in and out. The programmer now gets to work in the problem space, working on the actual issue at hand, rather than the low-level hardware-oriented solution space. And at the machine level, there is no loss of efficiency. The object code will be as good or better after the Ada compiler is done with this. Okay. Now, it's common to write code like this in C. You define a type to represent some physical property based on some available machine type. What can possibly go wrong? Well, for one, float can represent an awfully large range of values. So it's really good to program very defensively everywhere this is used. You want to code up checks wherever appropriate. And for the function, you really have to get either be really good at C, and either way, you have to get the syntax right. You have to, if you want to pass pass a pointer to the value, you have to make sure that all the syntax is correct. You have to specify const in the right places if you want some read-only properties, so on and so forth. Now, a similar thing in Ada looks like this. Ada does let you be a lot more precise about your requirements and expectations. First, instead of just using a machine type directly in the source code, we state the real world requirement that our application, let's say this application, requires 6 digits of decimal precision. So if we try to compile this code on a machine that doesn't fulfill that requirement, the compiler is going to bomb. And compilation errors are great things. Compilation errors are awesome. A compilation error tells you that something cannot possibly work. And in this case, that compilation error could possibly tell you this hardware can't fulfill your real world requirements. At this level of abstraction, you care about the correct calculations and you care about the correct results. Thinking about machine specifics that will probably change under you at this level of abstraction is not the kind of thing you want to be thinking about. Second, on the right here, we constrain the range to between negative 273.15 to 1000. And this is inclusive. And what this does is it provides more information about how this type is to be used. Our static analysis tools can check whether there's a possibility that will breach this contract in overflow or underflow. And by default, the compiler will automatically insert dynamic checks. So we have automatic defensive coding all over anytime this is used. In the argument list for procedure update, you see those two words. T is in, out temperature, and those two words are also significant. In describes this expectation that T has an initial value, all right? T has a valid value as an argument when it's passed into update. Out states that we expect that this procedure might possibly update the argument, all right? Now, the underlying mechanics of a subprogram colon eta versus a function colon C are exactly the same. The machine code looks the same. There's no difference at the machine level. At the human level, though, the programmer gets to be very, very precise and very expressive and state all of the requirements necessary. The compiler and static analysis tools have enough information now for both ensuring that everything is complete, consistent, and safe. And they also have even more information for generating more efficient code. Right. Here's one neat feature of the Ada language. If the processor that you're using doesn't have hardware floating point capability, but you still need to represent fractional values, Ada has a fixed point capabilities built in. And so here is our temperature type again. But this time, rather than specifying the overall digits of precision, we specify the precision as the smallest delta between two values. This delta can be a power of 2 or a power of 10. We also specify that we need to represent the same range of values from negative 273.15 to 1000. And what's really cool about this is, we're at the source code level, we're working with fractional numbers with decimal points. Under the hood, the compiler backs this using an integer type. And that integer type is going to have enough bit width to represent every value necessary. As a developer, you work with fractional values, but your processor hardware only sees integer operations. Now, Ada also includes modular types. In C, again, normally you would choose an appropriate machine type for representing values. And if you need certain properties, like you need to roll over at 360, because this is a number of degrees of angle, you need to babysit every single usage explicitly and manually. And in Ada code, on the other hand, what you do is you lay down all of your expectations in the specification. Once you do that, the compiler takes care of all of the hardware representation, the logic, and the arithmetic. The usage becomes very, very simple, and the tools ensure correctness. So here we have a next angle of type degrees, and we give it this initial value of the result of an arithmetic expression. And the compiler takes care of all the wraparound and all of the modular arithmetic there. Now, in this example, the code on the left in C, the code on the right in Ada are basically identical. All right, on both sides of the screen, we're setting up an infinite loop, and we call pull new data. If pull new data returns 0, it didn't do anything interesting, and we're just going to loop again. If it returns something non-zero, we break out of the loop. Every time pull new data doesn't get data, it returns 0. We're going to loop again. Every time we loop, we increment polling counter. And that's where the biggest difference is going to be. After a while, polling counter can possibly overflow. And if polling counter overflows, what happens? On the left side in C, we're looking at assigned integer overflow, and in C, that leads to undefined behavior. So what does that mean? Will it wrap around to negative values? Will it dump core? Maybe, it depends. In Ada, we do have runtime overflow checking that's enabled by default. Program behavior is fully specified. All right, so that's sort of what these languages, that's sort of what Spark and Ada looks like. And sort of, these are some of the nice things about Spark and Ada that you saw compared to C. Next, let's take one step further and take a look at what formal proof brings to the table. Formal proof, when Ada Core talks about formal proof, we're pretty much talking about Spark. Spark is a language that's a subset of Ada, and it's rigorously defined to make it possible to thoroughly analyze source code. So if you use Spark, you get a guarantee of correct data flow. For instance, it's illegal to use a variable before it's been initialized, right? No reads unless something's been written. It's illegal for subprograms to manipulate global data if you didn't declare that the subprogram manipulates global data. Everything really needs to be very explicitly declared as far as data flow is concerned. And that second line, you get a guarantee of the absence of runtime errors. If it's possible that you have a divide by 0 in your program's rejected. That's illegal. It's illegal for it to be possible to raise an exception. It's illegal for it to be possible to overflow or underflow or go out of bounds. Then interfaces. Interfaces of all kinds are really, really complete in Spark. You know, as I mentioned earlier, all dependencies, all your, you know, when you have a subprogram, all of your inputs, all of your outputs, they have to be explicitly mentioned. So, you know, you won't have things like unexpected side effects, and that's really cool. The really, really, really cool thing about being forced to be this explicit about all of your relationships is that now you have this super rigorous description of your program architecture in your source code, all right? Because the tools enforce it. The tools, in fact, every time you use them, they check all of your definitions, all of your specs for correctness and consistency, and they revalidate your specs. So you have a living document and a very correct picture of program architecture written right there in your source code. And finally, you can code up behavioral expectations. So we'll see an example in a little bit of this. You know, it's common if you have something like, let's say, a search function that, you know, if some item that you're searching for isn't found, the search function is supposed to return some particular value, like -1 or something. It's possible to actually code up that expectation. And then the tools can be used to help prove that the program does what you want it to do. All right. Here is a simple assignment to an element in an array in Spark. Now, the Spark prover will look at a line like this and ask lots of questions. Right here we have an index into an array. So is the index within the bounds of my array? We have arithmetic operations on the right. We have a multiplication. Can x times y potentially overflow? we have a division. The denominator z is z potentially 0. And then just the overall result of that operation, can x times y divided by z possibly be out of range? Can it possibly overflow? And on top of all that, we have all of these reads. Are all of these variables read? Are all of these variables initialized before they're actually used? Now, if the answer to any of these questions is unfavorable, your program will be rejected and you'll need to fix it. And that's a good thing. If your program passes, now you've got this guarantee of the absence of runtime errors. Another nice thing in Spark is the option of, in fact, encouragement to replace defensive code. So here on the left, we have a procedure spec and a procedure body. It's kind of like a function prototype and then the function implementation of a procedure next. And in red, you see some defensive code that checks whether this input, this iterator argument is valid. If it's not valid, you just don't do anything and this procedure will simply return. Using Spark, it's possible to shift the responsibility of valid input to the caller. So by adding this precondition, so you see that ADA aspect with pre, by adding this precondition and using Spark tools, you can prove that all calls that are made to this procedure are always made with valid values for that iterator argument. And now in the implementation, it becomes unnecessary to explicitly write defensive code. And finally, this here is an example of coding up an expectation of subprogram behavior. As foreshadowed, we have a find function that's going to search based on these three arguments. You pass it an array, a value to search for, and an index to start from. You don't want, maybe you don't want to search the entire array, you want to start from a particular index. Fantastic. We describe a precondition that says that the start value has to be valid. And given this precondition, we are guaranteeing the postcondition below that. Now, let me translate that postcondition to English, all right? I'll just read it in English. So if looking at all of the elements in this array, from the given start to the end of the array, if the value we're looking for doesn't exist, then, all right, and then we got that second line. If the value, if we can't find that value, then find tick results equals -1. This function should return -1. Otherwise, the value that we're searching for should exist in the array at the location that we're returning. Right? So it does take a little while to get used to the syntax, but you can get used to it. And the cool thing about once all of this is expressed, the Spark prover can be used against your program. If you code, again, if you code an implementation, given this spec, if you code a function body where these properties don't always hold, the postcondition is your program will be rejected. If you code an implementation where these properties are proven to hold, you have verified that the code functions correctly. All of this analysis is done statically, even before compile time. And if your program gets a green light from the Spark prover, what another really cool thing is you require no runtime checks at all in that final executable. The precondition, postcondition, range checks, all of that stuff, you can leave all of that stuff out because it has already been proven to hold. Many of our customers disable runtime checking because of this confidence in the proof. So you end up with software of very high quality with less runtime overhead and no need for defensive code. All right, so what makes Spark valuable? One of the coolest things is that it can be used by normal people. If you're used to an edit, compile, debug cycle, you basically just add proving to the mix. So it becomes edit, prove, compile. It's all done using one consistent language. The proof stuff, the specifications for proof are done using the same language as regular implementation code, namely Ada. The specifications can be debugged, and coders get to express and prove properties of their code using a workflow that they're used to. Spark provides some very, very strong guarantees of program properties, and it's possible to eliminate some kinds of testing and use formal proof instead. We have industrial customers doing just that. There are some things that are just impossible to test exhaustively, but which are possible to reason about logically. Testing cannot prove the absence of bugs. It can only prove the existence of a bug. With logical reasoning, you can have some very strong guarantees with lots of confidence. All right. So let's say you might want to get started using Spark, or you're Spark curious. Maybe you haven't started your project yet. Maybe you've got some existing code and you want to look at what you can do to get more confidence in that, or you want to add something. Well, what are some of the ways you can get going with Spark? Well, if you're developing new software from scratch, it's easy. You could just elect to use Ada and Spark on the entire application. But of course, most projects aren't like that. Usually, almost always, we build on code that's already been written and known to work that we trust. So to improve the quality of existing code bases, or to add quality modules to existing code bases, we have a couple of options. You could rewrite specific sections using Ada and Spark, or you could add new modules that have been written in Ada and Spark. Interfacing between languages is something that we're actually very familiar with, where we've done things like that since the beginning. And it's pretty easy to do. In broad strokes, normally, when you have a mixed language application with C and Ada, you would compile the C portions using a C compiler, the Ada portions with an Ada compiler, and then you just have a bunch of object files which you pass to a linker. Now, in the automotive domain, there's such a variety of processors that it becomes hard to maintain an Ada compilation system for every possible processor variant, and we still have a solution for that. If you're coding DSPs or using microcontrollers like Infineon's Tricore, you can program in Spark or Ada and run that code through an Ada to C compiler. And that Ada to C compiler is qualified to ISO 26262 TQL3. And so you've got, it will preserve guarantees in your Spark or Ada code. Now, after you run that through your Ada to C compiler, you have a bunch of C code which you feed through your existing hardware toolset. So there are compilers and linkers that work fine for multiple languages. Let's see what the source code looks like. Within the source code, interfacing between C and Ada is possible using standard Ada language constructs. For the C interface on the left, all right, you have a typedef struct pause, and then you have a void function move. The Ada analog to that on the right is an Ada record and an Ada procedure. All right, those are all equivalent. On the Ada side, we have these additional aspects that we add. So for the position, we add with convention C. And then for the procedure, we say with import convention C and external name is move. And what this does is this informs the compiler that these things in Ada are actually implemented, are actually connected to the C universe. And the compiler takes care of all the details of interfacing. We also provide automatic binding generators for both directions. If you have an Ada spec and you'd like to generate a C.H file, we can do that. If you have a C.H file and you'd like to generate an Ada spec, you could do that as well. All right, and now, how does ISO 26262 fit into all of this stuff that we're presenting? Well, ISO 26262 is a safety certification standard, of course. So there is a great deal of emphasis on having specifications and architectures that ensure safety goals. You have safe coding methodologies that are prescribed, and systematic verification is essential. The Spark language is designed from the ground up with these considerations in mind. Compared to MISRA C or other safety subsets, Spark is a full-featured language, and it can be used as is without any modifications to satisfy those safety requirements. And there, because it's so powerful, this can possibly result in a significant cost savings. Logically sound verification is a really special thing. The proofs you get can give certification authorities enough confidence to allow you to replace manual reviews and testing. All right. One of the fundamental ideas behind Ada and Spark is to respect that programming is a human activity. We want to leverage machines to do what machines do best and leverage humans to do what they do best. Compared to C and C++, Ada and Spark don't expect that safety comes from making developers constantly pay attention to low-level details manually. It's the machines that are good at bookkeeping. Machines are really good at logic. Machines don't get tired. So we let the machines perform all the super rigorous verification based on specifications that humans write in the code. The programmer gets to focus on good software engineering at the right levels of abstraction. And the tooling and language help achieve a high level of safety. In 2018, an independent study by VDC compared development costs by language. And in that study, using C as a baseline, it turned out that the use of Ada saved almost 40% in development costs. Some of the requirements in ISO 26262 are satisfied just by choosing Spark as a programming language. Fundamentally, just by language construction, Spark ensures, just by using Spark, Spark ensures that these requirements are met. Otherwise, the program is rejected. For instance, 1C, initialization of variables. If your program ever reads a variable before it's been written, that program is illegal, just as a language design fundamental. 1G, no implicit type conversions. Implicit type conversions don't exist in the language. You just can't express it, and so on and so forth. Now, for these tools that are important for qualification certificates are available. The GNAT Pro Ada compiler is qualified to ISO 26262 TCL3. The Ada to C compiler is called CCG, and that is also qualified to TCL3, as are the Spark verification tools. Now, the cool thing about the Spark verification tools being TCL3 is at TCL3, confers confidence in the replacement of tests by proofs. And if you, we are seeing some uptake of Spark and Ada in the automotive industry. We have studies happening and we have adoptions happening at all in various places. We have OEMs, tier 1s, tier 2s, and platform providers with an interest in Spark and Ada. The main domain of interest seems to be autonomous driving and driver assist systems. So we're looking at various levels, in sort of in the middle where we see interest in communication layers. So we're talking middleware kind of stuff. At the low level, where we see interest in safe drivers, sensors, and firmware. And then at a higher level is things like safety monitors around complex things like machine learning decision systems. A bunch of companies are starting to talk publicly about Spark. NVIDIA is one of the biggest splashes. They were looking at an application where they were worried about testing. There were safety and security aspects that they felt testing wouldn't really work for, not at a reasonable price anyway. So they were able to use Spark and formal proof techniques to achieve safety and security with a lot of assurance, with lower cost, without the crazy testing that they were afraid of. For Denso, Denso was able to apply formal methods to code up, safety critical high ASIL components. But not only did they do that, they were able to demonstrate freedom from interference from their legacy C code, as required by ISO 26262, and so on and so forth. We're not allowed to talk about everybody we know. Many of the actors are not public yet, and this is definitely still an early adopter market. Now, if you want to learn more, if you're a techie, I highly recommend, if you want to play with a prover, play with a compiler, learn the languages, we have a great resource called learn.adacore.com with really well done training resources. Using that, if you go to learn.adacore.com, you don't have to, download software and install compilers and all that stuff. You could just go to the website to see what it's all about. We have books available at adacore.com/books, like a migration guide, implementation guide for Spark that was co-written by us and by Thales. And we also have a book, Spark for the MISRA C developer, among other things. We have a blog at blog.adacore.com with interesting projects and stuff. And of course, you could always contact us at info@adacore.com. Thank you very much for your attention. I didn't go too
Yes,
fast.
Thank you very much. Thank you, Albert. I would say, unfortunately, we don't have a whole lot of time, but I think we'll have enough time for at least 2 questions or something. Thank you again for the presentation. I will just skip forward and hand you over the questions that we got. So one of the questions I think is in regard to the ISO 26262 that you were referring to later. So I think one was in regard to automated driving and the ISO regulation, what tasks can actually be replaced? I think overall, just yeah, a little bit more information in that maybe.
That's a great question. In specific, like testing for things like validity of data. I mean, as things get more and more complex, and the interactions become, with a lot more inputs and a lot more data flow, verifying the validity of data in a particular buffer and things like that possibilities. I don't know. That's just one example, but that's one of
No,
the,
sure.
yeah, when you're dealing with a lot of complexity, it's um, replacing testing like large buffers exhaustively is something like that is fairly impossible to do, because you just take 32 bits and you multiply that by a large memory space, and you want to test that entire space exhaustively. You can't do it, but you
Sure.
can reason about that kind of thing logically.
Thank you very much. The another question is in another space. You already highlighted what companies are already starting to use it. You said it's an early adopter market, but this question aims in what other industries it is used more often, and where is like I think the question aims in where is the main expertise so far.
Oh, I mean, we still, Ada Core's sort of pedigree comes from aerospace and defense. That's sort of where Ada Core started. We have seen very successful projects in medical. We have seen successful projects in banking, telecommunications, and heavy industry, industrial controls and automation. Uh, and so, yeah, we have seen interest in these various industries. Automotive is certainly relatively new for us, but we're seeing quite a bit of uptake and interest, and we want to expand into this market because we think we have something really, really useful and something that people will enjoy using. But a lot of our business right now is sort of that sort of aerospace. Oh, and I'm sorry, rail, of course. Rail is a very, very traditional, very big industry for us. Safety and security in rail is very important.
Thank you. I think that answers it very well. One last question I would put in, because otherwise, like afterwards, we'll head to our next speaker, who's already there. So the last one was actually how, I think you also already mentioned that. How easy is it to integrate existing codes written in other tools into Spark?
I mean, the interfacing itself is very, yeah. Just if you want to call one thing from another thing, that's super easy. That doesn't take anything. You could
I
write.
think it's more about the adaptation. Sorry.
Yeah, if you want to translate something
Yes.
existing into Spark, like any programming language transition, that kind of depends on the application, unfortunately. There are some things that, like really, there are some things that are easy to translate and prove functional properties about, and to prove absence of runtime errors. There are some other things that, when you're looking at proving logic, that you do have to express that logic, and there are some challenges when you are dealing with certain kinds of constructs. So yeah, some applications are more suited to others. The beauty of Spark is that the things that are understood for a software engineer, but that might be hard to do formally, you could still use a regular language. You could still use Ada. You could still use C. You could still use C++ for those portions. And then for the portions that you can formally code, you integrate Spark with that. And so that still brings up the confidence level and the safety level and the security level of your entire application. And one of our customers, yeah.
Sorry. Sure.
All
Sorry.
right. No, not at all. One of our customers, I believe it was Denso, was able to, in fact, use Spark functionality to add pre and post conditions to their existing C code. So they were able to interface using Spark. They were able to, in fact, improve some of their C functionality as they interfaced with that by setting expectations.
I think that answers the question very well. Unfortunately, we have to stop at this point, but thank you very much. Of course, to our attendees, I think in the last slides, there was already a hint where you can find more information. Other than that, if you, of course, still have questions, forward them to me, or I will forward them to Albert or text him directly. But thank you very much for your presentation, Albert, and yeah, thank you.
Thank you very much, and be well, everybody.